So we're going to continue with the frames and machines, and we kind of wrapped up yesterday's lecture with this kind of concept quiz thing. And, it's kind of noisy out there always. So we learned basically that to solve a frame, well, what distinguishes a frame from a truss is what? Yeah, trusses only have two force members, and frames, machines will have at least one multi-force member. And because you have a multi-force member, that sort of determines the reactions that we'll have on it. Going to have sort of independent at the pins or whatever. If there are pins, it'll have independent horizontal and vertical component forces reacting. And we looked at pulleys as well. And today we're going to look at interesting again, you can make all kinds of weird contraptions with pulleys and beams bent at different angles, and give all kinds of problems on what are the reaction forces inside that structure, what are the the support forces on the different members to maintain the equilibrium of that whole structure, right? So, and typically, we have the situation where sometimes it might be helpful to find the reaction forces. Sometimes it's not possible. Can we find the reaction forces before we start breaking this thing apart on this structure? Can we find the external reaction forces? Is it possible to find the external reaction forces on the structure without breaking anything apart? And when I ask that, what you can do is just forget everything. Just imagine this is a big blob with a weight hanging off of it. Forget everything inside there and look at the joints, the supports. Can you solve for those reactions right now, knowing what you know? Yeah, because one of them's a pin and one of them's a roller. And there's three reactions. You can set up the equations, you can do moments, you can solve it, right? So you could solve those. That's something you want to keep in mind, because you don't have to go into straight breaking them apart. But sometimes if all they're asking for is one thing, sometimes you can just go directly to the answer, right? So the reactions here, yeah, we're going to have an AX and an AY, and we're going to have a CY, but no, or a CX, but no CY. Now, sometimes you don't have that luxury. Like if you go back a couple slides, like for instance, this problem here, you had two pins. Each pin can conceivably have a horizontal and vertical force. Therefore, you would have four unknowns. Can't really solve for those reactions when you got two pins supporting the structure because you got too many unknowns. You can only solve for three unknowns in a 2D structure, with the equilibrium equation. So you can't do it on that one, but you can do it on this one, because this one, although it has two pins, this is a two-force member. So again, that's only one unknown. And well, actually, you can sort of just break it apart. You don't really need to do the reaction. But anyway, yeah, that's the kind of awareness that you have to develop when looking at these problems. So first, if you can solve for the reactions, it seems like a reasonable thing to do. We'll go ahead and do that. So we can do the free body diagram for the whole frame. And so that's step one. And then step two is to analyze those reactions. So we're going to find that, the sum of the fy's equals 0, and that's going to be basically just ay going up, and this weight is 120 newtons, so we're going to say minus 120. That's this guy right here. So ay is 220 newtons. We could also find the sum of the moments at A. Set those to 0. That's going to be Cx times 0.4 meters minus 120 times 0.6. And that'll tell us that Cx is equal to 180 newtons. And finally, the sum of the fx's equals 0 is going to tell us the Cx plus ax equals 0, meaning ax equals minus 180 newtons. So again, if you can do it, go ahead and do it. If you can see that you can solve for the reactions with the supports given, then go ahead and do it. So step 3 is we're going to need to sort of dismantle the frame. And do we have these things on here? No, we're going to have to draw these little components. So we've got a L-shaped piece, ABC. Or ABD, I guess. And we've got this other thing here called BE. And we've got a pulley. And we've got this other piece called CDE. And at E, there's some interesting stuff going on because with E, you have 3 things coming together. Remember how I said sometimes you're going to want to do the free body diagram of a pin in order to kind of keep things sorted out properly. With point E, you got 3 things happening. So it can be a little confusing on how those things all relate. So we might want to do a free body diagram of the pin at E in order to really understand what's going on there. Okay, because there's 3 things coming together. So you've got 3 different reaction forces, 3 sets of reaction forces, or does that make sense? There's these 3 things that are going to have their own reaction forces that they're going to be sort of dealing with, right? These 3 things coming together. And that's a good indication that you might want to diagram the pin. Okay. These other joints, there's only got 2 things coming together, right? So they're simpler. Okay, so what's going on member ABD? What's happening on ABD? Well, we got the reaction forces AX, we got AY. There's this tension force which is acting on this guy, so you can do a T there. And member BE. Member BE is a 2-force member. That's nice. We can assume that it's in tension. I guess that's probably reasonable because that weight is going to be pulling down, wanting the thing to flip that way. So you're going to have a BE over here on this guy, and then we're going to have some reactions at D. Now, what kind of reactions are we going to have at D? Is it just a single reaction where we know the direction, or are there 2 independent horizontal and vertical components for the reaction? There's 2. How do you know that? restricting two dimensions because the thing that's attached to it is a multi-force member as well, right? So when you have a two-force member, you only have one unknown coming in. So like BE here is a two-force member, so there's only a BE along the direction of BE. But with point D, you've got a multi-force member here, which is CDE acting with forces on it at multiple points beyond 2. So therefore, you have to assume that there's going to be an independent dy and a dx. And we can have a dy going this way and a dx going this way. It's fun to try to figure out which way those forces are really going, but most likely you're going to make mistakes. Don't worry about it. Just be consistent with your arrows. Okay. Now, so that's one of the members. How many unknowns are there? Well, we solved for A's already, so there's just dx, dy, be, and we know t because that's 120 newtons. So there's only 3 unknowns on there. We could solve for those. We could solve for all the forces on A, B, D right now if we wanted to. But we'll figure that out later. So BE has just a 2-force member. It is just a 2-force member, so it only has these forces. Now remember, when you transfer from the reaction of this member BE on ABD, it's going to go to the right, so we have to do it going the opposite direction on member BE. So this is the direction on BE as if the member BE is in tension, right? It's like it's being pulled. And so if BE is being pulled, like it's stretching, it's going to try to keep member ABE, try to make ABD make that go to the right, so it doesn't have to move. And looking at the member CDE, we're going to have this CX force, the reaction force, C. At D, we have to flip the direction of the reaction arrows that we drew on ABD. So those have to be in the opposite direction, right? So you have to have DX, you have to have DX going to the left, and a dy going down. I'm going to move my D a little bit. And at E, we have an EX and an EY, right? Because there's 3 things coming together there, right? There is a 2-force member, but there's also that pulley, and those things are going to provide a whole bunch of interesting reactions going on there. So at E, we're going to say, okay, well, we're going to have an EY, and we're going to have an EX. Now the pulley is kind of interesting. Actually, yeah, the pulley is interesting. So we've got BE coming here, we've got EX and EY coming there, now we've got the pulley. Let's look at this pulley. The pulley is going to have tension forces, tension force going to the left and down. I think I'm going to move my point E a little bit. Well, I think it's okay there. And we're going to have, what's going to keep the pulley from going left and to the right? EX and EY. But there's also this BE there, right? So we have to think about all these things. And so the EX and EY that's acting on member A or member CDE is not necessarily going to be the same as the EX and EY acting on the pulley, because you got this other force, right? You can't just flip them, right? So what you can do, though, is come up with new variables and say, oh, well, let's just assume there is a PEY. We'll say PEY for the pulley, the EY for the pulley reaction, and a PEX. See how it gets complicated right at that one point, because there's three things kind of tied together right there. We have to kind of understand all of those. And now we can draw those on pin E to kind of make sense of what's actually happening. So if PEY is pushing up on the pulley, then PEY is pushing down on the pin, right? PEX is pushing the pulley to the right, then it is also pushing the pin to the left. Now we also have BE pulling member BE to the right, so it must be pulling must be pulling the pulley to the left. And we have EX pulling member CDE to the right, so it must be pulling the pin to the left. So in every case, we are flipping the polarity of the reaction forces when we move to a connecting body. And when that connecting body is a pin, we apply it to the pin. So the EX is going to the left, EY is going, oops, I forgot that last EY is going down here. The pulley, when the pulley is connecting to the pin, whatever reactions that the pulley is feeling are equal and opposite on the pin. Whatever member BE is feeling, whatever forces, reactions, then it is doing the opposite to the thing it's connected to. Okay, questions? So now we can look at what we're supposed to solve. Well, we're supposed to find the forces on member CDE. Can we solve for that knowing what we now know? If we look at member CDE, do we have a way to solve for those reaction forces on CDE? There's 5 of them. We already solved for CX. Can we solve for the other 4 right now? Too many unknowns, right? Can only do 3 unknowns, so we're going to have to start somewhere else. We can't solve for the forces on CDE yet until we solve some of the other ones somewhere else. And we did notice as we were doing member ABD that there are only 3 unknowns now that we found the reactions, so we could start the analysis there. And once we get the answers for dx and dy, we apply that to member CDE, and then we can solve for just the remaining forces at E. And that's how we'll find out what's acting up on member CDE, right? So we go to the next page, and we start on analysis on member ABD. And I guess we will, I have room here so we can kind of redraw this free body diagram. We've got AX and AY. And we know AX is minus 180, so we could actually replace AX and AY with the actual forces, right? If we have a minus 180, then we've got a 180 going to the left, which is our AX, and our AY is 120, so we've got 120 going up there. And we've just got, oh, and T is actually, we know T is 120 as well because of the weight. So those are the 3 unknowns, BE, dx and dy that we have to solve for. So we do the same equations of equilibrium. Sum of Fy is equal 0, and that equals AY, well, which is basically 120 plus dy. We drew that going up. And that means dy equals minus 120. And if we do the sum of the fx's, this is pretty easy. Sum of the fx's equals 0. Means we're going to have 120. Oh, but we don't know BE yet. So, well, we can write it out anyway. So it's 120 plus BE plus dx. Minus 180, thank you very much. 120 plus BE plus dx minus 180. Well, we could noodle around through here. We could solve for it, but we also could realize that having just solved for dy, we now only have 3 unknowns on number CDE. So we could just do the rest of our analysis on that number. It might be a little bit easier, I don't know. But that's what my solutions have. This is the fun thing. There's often more than one way to solve a problem. But I'm going to go with what I have on my slide here because I don't want to go off into Never Never Land, which I've done before. So we're going to move to member CDE. And member CDE now has, it has a CX, which is 180. It has a dy and a dx. Now we drew the dy. Let's draw the dy, even though we solved for it. The dy is going down, and the dx is going to the left. And it has an ey and an ex. Now, number CDE, if we do the sum of the moments at E, and we already know dy, we can solve for dx directly because we know cx and dy. So we can do that. So we can do the sum of the moments at E equals 0. That's going to be cx times 0.2. What else is going to give us a moment about E? dy, it's a moment arm, 0.4, and positive or negative? Are you sure? Positive, okay. Because you're looking at how it's going to cause a rotation counterclockwise about E, right? And Paul, you want to give another moment? What's going to give us another moment about E? Okay, moment arm. dx times 0.2, positive or negative? Okay, I agree with that. And now we know dy, so we can just solve for dx. dx equals 180, which is our cx, 180 times 0.2, plus dy, which is minus 120, times 0.4, all over 0.2. And so dx is going to equal minus 60 newtons. And we have some of the fx's equals 0. It's going to give us a cx, an ex, and a minus dx, And that means EX is going to be minus 240. CX is 180. DX is minus 60, so minus and negative 60. Yep, that gives us 240. And it's minus. And then the sum of the FYs equals 0. That's going to be EY minus DY. So therefore, EY is going to also equal minus 120 newtons. Okay, questions? So this is the beginning. Now, if you were actually, gonna build this thing, so these reaction forces, you might think, okay, big deal. What's the point of these reaction forces? Well, with these reaction forces, you can now, as we're going to see next week, we're going to be looking at what the internal forces are inside that member as a function of X or across that whole beam. And those internal forces are affected by the reaction forces. They're causing warping and bending, tendencies of that material. And this sort of ties it in with the materials engineering course. And then later when you do a strength of materials course, if you do that for like civil or mechanical, it will also give you more insight into that. So you can then use this information to design this contraption so that it doesn't break given the loads that you expect to put on it, right? That's the whole point of why we're doing all this stuff. We're analyzing this stuff so that when we do a design, we can make sure that our design is going to be effective, right? And likewise, if you want to do that design thing, remember that design, that truss design, that's, I'll hand out something I think next week on that, but you can tackle that if you want. It'll give you a real good motivating info for learning these analytical techniques. And the last example for today is going to be a set of flyers. Although there are some more that we can look at, so it's fine. Yeah, you can get some really interesting mechanical arrangements with these pliers, vice grip type things. And the problem is asking us to find the forces acting on the bolt. And that bolt is being gripped by some pliers, and the forces are acting right at it. It's in the jaws. It's being compressed. So we're just asked basically to find the force E that the pliers are giving to that bolt. And the hands are gripping. There's a grip of 150 newtons on those hand grips, and the dimensions are all given to us. These look really intimidating. Not having done any of these before, you might find hard pressed to. I always like, oh, well, that looks really hard. But if you can start looking at this thing, you might notice a two-force member in there, and that might help you relax a little bit, right? Do you see the two-force member? Yeah, member AB. So that's just one unknown. And then, as usual, we break apart the structure into its individual pieces, and we label the reaction forces acting on it, right? And since AB is a two-force member, that's one unknown. We just draw that reaction going along that line AB. And we have this, the point where A and B are connecting. That's just one unknown. But then, where C is, you've got this pin where you've got two multi-force members coming together. So you're going to have a CX and a CY there. With this pin down here, again, you have two multi-force members, DX and a DY. With this bottom jaw here, you've got those other forces kind of coming across like that. There are no so nice about this one, there's only ever two things coming together, not like the last problem where you had three things coming together. So it's not that hard. And as a plan of attack, if you look at member BD, so you can kind of study member BD. If you look and do like the sum of the moments, since what's nice about having a two-force member, you can isolate that in a single moment equation, like about point D, right? So if you did the sum of the moments at D, that would allow you to find R. And knowing R means you only have three forces on member ACE, right? So if you do that, and you do the sum of the moments, say, at C, what comes out of there? If you do the sum of the moments at C, what are you going to get? What new information are you going to get? What's the what unknown if you do the sum of the moments at C? E, yeah. And that's what we're trying to find. So that's the approach you can take to solve this. You can find the sum of the moments about D on member BD, find R, and then use that information to do the moments about C and find E. That's all you really have to find. There's a lot of other forces acting in there, but you can ignore those, because all we're trying to do is find the force on that bolt. So that's the high-level plan. Now we just go and implement the plan. So we do the sum of the moments. That thing going to be there? Yeah, so the sum of the moments on BD, sum of the moments at D is going to equal, and you've got a 150 times this distance 130, so 150 times 130, and that happens to be clockwise, so we'll say that's negative. And this R force is at an angle, so that's a little annoying. But this is where you have to know a little bit of you have to have a little more experience. If you actually break this thing up into its components, you can avoid doing the trig. Well, actually, basically, Ry is what? I was asking you to tell me what Ry is in terms of R. What is it? It's just R sine of alpha, right? Yeah. It's just R sine alpha. It's not that mysterious. So you can think about that. Is R cosine alpha going to give you a moment about D? No. So the only thing we really got to worry about is R sine alpha. And it just turns out that we actually never need to know the horizontal part of R. So the way these things are aligned, right? That's actually a convenience of the problem. So if you just want to write about that as an Ry, the moment arm for that's going to be 30. And it's counterclockwise, so that's positive. So this allows us to just solve for this unknown Ry as 150 times 130 over 30. So that equals 650 newtons. And member ACE. If we do the sum of the moments at C, we also don't have to worry about the horizontal component of R, although we could find it now that we know what Ry is. You could actually use like tangent or whatever to find Rx. But we don't need it. We do the sum of the moments at C, and that's going to have in it the 150 Newton on the grip times 130. And an Ry times 100. And that's minus. Plus E times 30. So we can now find the force on the bolt. It's E equals Ry times 100 minus 150 times 130 all over 30. And that's going to give us 1516 newtons. So we apply 150 newtons, and the bolt feels 1516 newtons. The ratio of those two is what we call mechanical advantage. This is actually a really important concept in machines. All machines are kind of built generally to have some kind of magnification of forces. So that mechanical advantage is defined as 1516 over 150, which is approximately 10 to 1. So those pliers are giving you a force multiplier on your hands of about a factor of 10. So that's pretty impressive set of pliers. Give you 10 times the grip strength of what you got. That's why we use them to unloosen bolts and stuff. Now, if you're taking circuits, mechanical advantage is the same thing as gain in a circuit. So Alex, you were in circuits. We often, towards the end, we're sort of looking at what the gain is of a circuit, how much it's amplifying a signal. Same type of information. We like to kind of make things bigger or smaller with mechanical or electrical systems. There's one more example. We don't really have time to solve it, but you can kind of see, you know, how things can get, right? They can get really complicated. We're going to be starting with fairly simple ones, but this one is talking about a crane to support a load of 700 pounds. And we're supposed to find the force in the cable at the winch motor W. And the horizontal vertical components of the pin reactions A, B, C, and D. Now, I think we can find the force in the cable at the winch motor pretty easily, kind of by inspection, right? Based on what we did yesterday with pulleys. Can anyone see? Anyone have an idea what you might think the force on the motor, on the winch motor, the force in the cable at W is going to be? 350, right? Because that pulley right here, right, has to support, you can kind of just do that in your head, right? It's got to support 750 or 700 pounds. So it's going to have 350 on either side of it from that cable, right? So that cable's going to have a tension of 350 pounds. Of the pin reactions A, B, C, and D, that's a little bit trickier, but you know, so A is just the you know, there's a horizontal and vertical component. D is a pin, but it's actually DB is a two-force member again, right? So there's only going to be a force pulling that guy apart, right? At D, or yeah, right. That's all that's going to be. And you can find the vertical and horizontal components of that. Then you got B. B is an interesting spot because B has three things coming together again, right? So that's where you would have to diagram the pin. And C, I'm not so sure about C because I don't know how that rope is fastened. You think the rope is obviously fastened to the pin, isn't it? So the pin at C must have three things as well. It's got a pulley, this beam, and then the rope, I guess, is attached to that pin, right? So that would be something to diagram probably separately too. Well, here's the solutions. So you can see that's what we expected for the pulley, and that was pretty simple. And then the diagram of the pulley at C is going to have the CX and CY. So you can, yeah, once you know the force on the cable, that's pretty nice. You can just solve for that, 350. And the pulley at B has this interesting angle there, and that's going to affect the BX and BYs. Okay, so in this case, the Bx is going to be 175 and the By is going to be 303. Interesting. For equilibrium, because of that angle, right? And knowing all that, remember BD is a two-force member. That pulley is going to be applying to ABC, those reaction forces that it was feeling, but the opposite direction. Same for this pulley. And so you got 350. And notice they have 700 here. What's that 700 doing? There was only 350 on that pulley. The pulley at C only has 350 going down. How come they got 700 over there? That's this other rope being attached to that pin, right? They just sort of gobbled that up in that 700 pounds. You see what I mean? So it's sort of being, aware of how that's working, being careful not to forget anything. And once you've got all those things labeled, you've only got 3 unknowns now. The red forces you can solve for TBD with the moments about A, and then AX and AY, like so. So they didn't have to specifically diagram the pin per se, but they had to be aware that there were things going on here. So like here is where they drew all those reaction forces kind of acting on the beam here, right? You got the BD acting on the beam, and you've got the pulley acting on the beam, and just making sure that you're doing the equal and opposite flipping when you move it from one body to the other. So and then they're finding the X and Y components. So good. So that's basically it. These are actually where it really gets kind of fun, I think, for me, because up to this point the problems are somewhat formulaic, where you just sort of follow, the same procedure. Now they're getting to the point where there may be multiple ways of doing this. You could go this way, you could go that way. This is kind of how it is in circuits. So when you get to circuits, there's so many tools to solving a circuit that you can sometimes solve it like 3 different ways. And so my predecessor always told me statics is a good preparation for circuits because it kind of builds the discipline of the method, but then circuits kind of takes it a little bit further because there's a lot of ways of going, and it makes it more interesting to me. Anyway, any questions or anything before we wrap it? So tomorrow we'll be doing some in-class problems, and nice, we got 2 days to do these, so we'll crank through as many as we can.